All right, this is a very common type of question. It shows up in all kinds of tests over the years. You'll face this one. And I'll set it up for you with a picture. We're going to start with a charge here, and this charge will be a positive charge. And we'll call it a 4 microcoulomb charge, positive 4. All right, so I'll put a positive in here just to remind you that it's positive. And then over here, we're going to have another charge, which is also positive, and it's going to be a 2 microcoulomb charge, 2 microcoulombs. All right. Now, the question that we're going to ask ourselves is, where could a third charge be placed? I'll change that, so that it feels a net force, or it experiences a net force of 0. Zero. Question mark. I'll also give you some indication of how far apart these are. So we'll give you an original distance of, I think, 0.5 meters is the example I'm going to use. So in other words, we're taking a third charge. I'm going to use a little red blob for this third charge. But we're going to put this third charge anywhere around this scenario. And we're finding out where would you put it so that it would experience a net force of 0. In other words, all the forces acting on it would cancel out. So we're going to mess up this diagram a bit. Let's look at some of the possibilities. Well, let's say we thought about all the area sort of up here on top of the charges. Let's think about that. If I stuck a charge here, right, any charge, and you'll see that it doesn't matter. Let's pick a positive charge. Let's put it right here, blob, right there. If I put one there, then if it's positive, it would be repelled from the 2 microcoulomb charge this way. There'd be a force pushing it like that, right? And it would also be pushed away from the 4 microcoulomb charge, something like that. Well, there's no way you can add these two vectors to get 0. Their horizontal components might cancel out, but their vertical ones won't. They're both up. So obviously you can't get an answer to the question by putting it here. And if you think about that same logic, even if you put it over here or anywhere up here, you're going to have forces that are pushing. Here's the 2 forces pushing that way. Over here, you got this one pushing that way and one pushing this way. Over here, this one pushing this way. And so you'll never get a 0 force up there, will you? And of course, by the same logic, if we look at the area down here, underneath, it's the same idea. If we go with another charge over here, well, it would be repelled from the 2 microcoulomb charge and repelled from the 4. Anywhere over here, repelled from the 4 and repelled from the 2. There's no way that we can get those vectors to add to 0. Now, what if we changed it? What if we made it a negative charge? Well, the only difference is the arrows would all flip their directions. So if that were the case, they would simply be attracted to here and attracted to there, or attracted to here and attracted to there. But again, these arrows cannot add to 0. And the same on the bottom, attracted to the one over there and attracted to there. So it doesn't matter what kind of charge is on this third charge, whether it's plus or minus. None of these areas will work. Okay, let's look at another area. Let's look at the area over here on this side. Well, in fact, let's look at the area right in here, because we've already talked about the top and the bottom areas. Let's put our little charge here and see what happens if I put it here. Well, it's positive. It'll be repelled from one of the charges, but also repelled from the other. There's no way it can be 0 there. And if I go to the other side, and I consider it over here on this side, linearly sort of going that way, It's the same problem. I put my charge here, it's repelled this way, and it's repelled that way. This leaves me with only one spot left, the area in between the charges. And so if I put my charge somewhere in between, let's say I put it here, it would feel repelled from the 4 microcoulomb charge, and it would feel repelled from the 2 microcoulomb charge. And it is quite possible that there's a place where those two could cancel each other out. In fact, it would have to be a little further away from the 4, because the 4 is a bigger charge, so its charge would extend over a greater distance, right? So where I've drawn it right there looks pretty close to where it probably would be. So what we want to do is find out where these two forces are equal to each other. We want to find the spot. That's our goal. So we know now that it has to be somewhere in between, and it has to be a little closer to the 2 microcoulomb charge, because we've eliminated all the other possibilities. So let's redraw our picture without all the craziness around it, and just kind of start from scratch. So here we are, and we have 4 microcoulombs here, positive charge. Over here, 2 microcoulombs, positive charge, with a distance between them of 0.5. And we're going to place our charge, our imaginary sort of other third charge. Well, there it is. It's not imaginary, it's a charge. And I'm going to call it little red q. And it doesn't matter whether it's positive or negative. It doesn't even matter how big it is, because we're going to see that all that will disappear. In fact, it's going to disappear completely from our math. All right. Now, let's talk about the distances that we have involved. If I put my q there, then the distance from here to here would be, I'm going to call that the distance between our q and the 2 microcoulomb charge. So I'm going to use a little subscript 2 to show that it's going with this guy. On the other side, we have the distance here, and I'm going to call this the distance for the 4 microcoulomb charge. So I'll use a little subscript 4 to show that that's the r for between q and that guy. So far, so good. And now what we're going to do is we're going to ask the math to help us out to solve this problem. So we're going to ask the math this question. Where are the charges the same? Now here's the problem. When we start doing math with the pluses and the minuses, things get a little bit mixed up, because with electricity, plus and minus really only indicates attraction and repulsion, not necessarily left and right. So what we're going to do is we're going to take that out of the picture and not be confused by it, and ask the math this question. When are the magnitudes of each force the same? That way I don't have to sweat too much about my directions. Magnitudes only. So we know there's a force associated with between Q and the 2 microcoulomb charge, and there's a force associated with Q and the 4 microcoulomb charge. And we want to know where are they the same. So how do we say that in mathematical language? Well, what we say is, let's take the force. Well, you know what? I'll write it as force first. Let's take the force between Q and number 4. That's how I write the subscript. Force between Q and 4. And we want to say that that's equal to the force between Q and the 2 microcoulomb charge. Written as it is, these are vectors, so they have directions. So what I do in math is I use the absolute value signs, which basically is a mathematical way of saying, don't worry about the direction, just figure out the magnitude of these forces. And when I put these absolute value signs on, essentially what that does is it means I'm taking the positive value of both of these, which means I don't care whether the charges are positive or negative anymore. I'm just going to put in the amounts for the charges, and I'm not going to worry about whether they're negative or positive any longer. So I'm going to put here K, Q Q1, which would be the 4 microcoulomb charge, multiplied by our little mystery Q3. I'll put him in red to remind you that's who he is. K Q1 Q2 over, and this would be, because I'll put a little 4 here too. Because I'm doing number 4, I'm doing also R4 squared. And that absolute value, or the positive magnitude of that, is going to be equal to the positive magnitude of K. This time I'll use little Q2 and my mystery charge Q. And this distance was R2. So the little 2's are just showing you that this guy over here is all about, this guy's all about the 2 microcoulomb charge, and this guy over here is all about the 4 microcoulomb charge, right? That's all about. But look what the cool things can happen here. There's a lot of things that are going to cancel out of this. Okay? So the way we do absolute value is we just forget about everything that isn't that's negative, and we turn everything positive. So all these numbers are rewritten now, but with the understanding that we're just looking at the positive values of them. That's what absolute value does for us in a sense. So there we go, and here's our little q, and then here is our R2 squared. That means that if there's a negative charge, it doesn't matter, right? It's a positive charge, it doesn't matter. All right. Now, I can put in some numbers, but before I do, I'm going to cancel some things out. I can divide both sides of this equation by k, and the k is gone. I can also divide both sides of this equation by the mystery charge q, and it's gone. So it doesn't even matter. Everything else, though, are different numbers. So I'll put those numbers in now. Q4 was 4 microcoulombs, which is 4 times 10 to the negative 6. And then R4 squared. And over here, this was 2 microcoulombs, so 2 times 10 to the negative 6, R2 squared. Now I'm going to do another canceling. I'm going to multiply both sides of this equation by 10 to the 6, which means if I multiply both sides by 10 to the 6, I can even get rid of all those decimal places. And I get a very simple looking equation that says 4 over R4 squared equals 2 over R2 squared. Okay. At this point in the question, there are 2 different ways we can proceed. And so I'm going to show you both ways. And there may be advantages to one or advantages to the other, but I'm going to show them to you both. Okay? So the first thing we're going to do is sort of divide our page in half. Because what we're going to do is take this over here, and we're going to take it over here. Right? So there's the page divided in half. If we proceed with this on the left side, the one way to deal with it is to cross multiply. And we would get 4 times R2 squared equals 2 times R4 squared. Make sense? Divide both sides by 2. 2R2 squared equals R4 squared. If we take the square root of both sides, we would get root 2 times R2 equals R4. Okay, let's move down a bit. What are we going to do with that? Well, there's not much we can do at this point. We have 2 different variables. But if we go back to our equation, I'm going to put a little but here. If we go back to our original picture, you will recall that the total distance between these two was 0.5. And if we're stuck in the middle, in fact, maybe I should go back so we can look at it. If we go right back to the beginning, we'll see that R4 and R2 added together must equal 0.5. So we can use that information as a way to help us solve this problem. So let's go back down to where we were, and we'll sort of remember that R2 plus R4 is the total distance, 0.5, which means I can say that R4 is equal to 0.5 take away R2. And I can substitute that into where the R4 is. So now I have root 2 R2 equals 0.5 minus R2. All right, well, root 2 is just a number. We can figure that out. So if you go to your calculator and you take the square root of 2, here's what you get, 1.41. But I want you to remember something that we often forget about square roots. 1.41 times 1.41 might equal 2, but so does negative 1.41 times negative 1.41. When you square root, you always get two answers. We always forget that. We learn it in grade 7, and then we just start square rooting and taking the positive root all the time out of habit. But there's two ways that this could work out. So now I have to work it out two different ways to see what will happen, and I'm going to end up with two different answers. But that's okay. We're expecting that. So how do we work it out? Let's try the positive one. If I use the positive value, then I'm going to group my like terms, and I'm going to have plus 1.41 R2, and then add another R2 because I'm moving it to the other side, and that'll equal 0.5. Right? So this will be 2.41 R2 equals 0.5. And then by division, I get that R2 is equal to, so 0.5 divided by 2.41 comes out to 0.2-ish. Or I have to consider the other option where I'm going to use negative, negative 1.41 R2 because I have two options. And if I consider this option, then when I put everything together here, it's going to be negative 0.41 R2 equals 0.5. And this time, so it's 0.5 divided by 0.41. It comes out to R2 equals negative 1.2-ish. Now, we have two answers. The question would be, why two answers? What does each of these answers mean? Any ideas? You're right. One's on one side and one's on the other because one's a negative number. So remember, the negative just means opposite. It doesn't necessarily mean to the right or to the left. It simply means opposite. So what we'll do is we will leave that for a second. We'll look at the other possible way of figuring this out. And then we'll come back and explain why the two answers are there and which one is the answer that we want. So let's go back up here to where we were going to do a different solution. What we're going to do is, in order to do this, I'm going to redraw our picture rather than keep bouncing up to the top. So we had 4 microcoulombs here and 2 microcoulombs here. And here's what I want to draw. Here is the 0.5 between them. Here is our mystery charge spot. And what we had said was we were calling this R2. That's not a very good 2, is it? You can't hardly even see it. Like that, a little bit bigger. We're calling this R2. And we were calling the distance over here, from here to here, R4, distance to the 4. Well, instead, what I can do is I could call this R2, just call it X. And if I call it X, then R4 becomes 0.5 take away X, doesn't it? Because it's the entire 0.5 minus the X, which puts me right here, where I want to be. And then I can, write that into my equation. So I've already solved it this far, right here. Everything's the same up to here, but now I'm going to put these numbers in. So for R4 squared, I'm going to have 4 divided by 0.5 minus X squared. That's my R4 right there. And then for my R2, I'm going to have 2 divided by just simply X squared, which is this guy right here. And then I'm going to proceed to solve this. Whoops, I went crazy there. I'm going to proceed to solve this using the mathematical skills that we have. You can find it. First we'll cross multiply. 4x squared equals, now what's this going to be? Well, it's going to be 2 times. At the same time, I'm also going to square this binomial. If you remember how to do that, using FOIL. So 0.25, then it'll be minus a half x, which is minus a full x, and then plus an x squared. So far, so good? If I make a mistake, yell. 4x squared equals, multiply the 2 inside, 0.5 minus 2x plus 2x squared. Let's put everything on the same side. If we move everything over to the left side, I'll have 2x squared left over, 4 take away 2. I will have a plus 2x, whoops, not an equal sign there, sorry, plus 2x, because it's moving to the other side, and a minus 0.5 equals 0. Now, if we do the magic of QRF on this, I won't write out all the QRF, but let's just do it. We would have 0.5 times 2 times 4 is the 4AC. And of course, it will be a positive number, and then plus b squared, which is 4. So what we end up with is if we do QRF, we get negative 2 plus or minus 8 over 2a over 4. That's kind of what I got. So if we have negative 2 plus 8, our two options are 6 over 4, negative 2 plus 8, or negative 2 minus 8, negative 10 over 4. Well, 6 divided by 4 is, uh-oh, we have a problem. We should be getting the exact same answers. Did I make a mistake? Let's double check our QRF here. 0.5 times 4 times 2 equals 0.5 4AC times 2 times 4 equals, yes, it's not 8. Sorry, I did make a mistake, which is exactly what I didn't want to do. I'm 2 for 2 now because I made a mistake on another video as well. The discriminant comes out to 4. The b squared minus 4ac, I believe. Is that right? Are any of you following along here? Am I good so far? You've checked it out? So it's actually going to be what? Is that going to give us the right answer now? Negative 2 plus 4. Still not going to give us the right answer, is it? Negative 2 plus 4 is going to be 2 over 4. To the half. All right, you know what we're going to do? We're going to pause this for a second until we figure out what we're... All right, so the lesson learned here is not to do QRF so fast. If we'd written it out and done it carefully, I wouldn't have made the mistake. The discriminant, so we got negative b plus or minus the square root of b squared minus 4ac over 2a. I was trying to do the entire discriminant in my head, or with the calculator to save time, and I got it wrong twice, so we lost time. So better to just write it out. It turns out that the discriminant then is negative 2, and it's not 4 or 2. I forgot the square rooting, and I did everything wrong. It's 2.83 is the discriminant divided by 2a, which is 4. So that's what we really have. And when you work this thing out, you get two answers. 4, negative 4.83 over 4, correct? Which is, if we do 4.83 divided by 4, it gives us about 1.2 negative, which matches the answer we got down here. Or the other option is negative 2 plus 2, so it would be what, 0.83, right? Over 4. And 0.83 divided by 4 is about 0.2. We got a little bit of a rounding issue there, but it's close to 0.2. So that matches the answer we got over here. Needless to say, the first method is probably less prone to error and less problems with the QRF and making the mistakes. But that was my mistake for trying to rush, not your mistake. You would have done it nice, and shown it all and worked it out. Okay, so now we have to talk about these two numbers and what they mean. So let's go back and draw our original picture again. here we are, here and here, 2 microcoulombs, 4 microcoulombs, and a distance of 0.5 in between. Now in our original picture, we said that the distance here to our mystery charge Q, in our original solution we called that R2. And we also called this distance over here R4. We solved this and we got a value for R2. So let's look at this right here. The two values we got for this answer are negative 1.2 and 0.2, right? So which of them makes sense? Well, if you have negative 1.2 for this value, you would have to start here and you would have to move a distance of 1.2 meters away, which would be way over here somewhere or way over there somewhere. Neither one of those answers lies between the two charges. So that can't be the answer to our question. Because our question, we had pinned it down to having to be in the middle. Remember? So that means that the only answer that makes sense is the 0.2. Because if this is 0.2 right here, then, and you subtract 0.2 from 0.5, then that means that over here would be 0.5, take away 0.2, which is 0.3. And that makes sense. It looks like it fits. That's exactly what we would expect. So if the answer is 0.2, why is the math giving us two answers then? Why not just give us one answer and stop confusing us? Well, we have to go back to what we asked the math in the first place. And instead of going back, I'll just rewrite it. We asked the math specifically to tell us when the force between Q and the 4 charge, was equal to the force between Q and 2 in magnitude only. And the math said, well, sure, I can help you with that. There are two places. There's the place in the middle that we found, right here, right? Which I'll draw it again, because that picture is too confusing. There's the place we found, there's our 4, there's our 2, and we put our Q right there. And that was the 0.2. 0.2 away from this charge. Okay. Well, what does this other number mean? Well, here, there's a repulsion this way from the 2 microcoulomb charge, and a repulsion this way. Or if we assume a negative charge, it would be an attraction and an attraction, but the same amount. So the math says, here's one spot where the value of this force is equal to the value of that force, the magnitude only. But there's another spot, and it happens to be a distance of 1.2 meters away, right? So let's think about that. 1.2 meters could be sort of way over here, or way over here. I can't draw it to scale because I'm off the screen. What would that mean? Well, way over here couldn't work at all. Because as you move over this way, you're always closer to the big 4 microcoulomb charge. So the force of the microcoulomb charge will always be stronger than the 2 microcoulomb charge anywhere on this side, right? Because you're closer to it. But over on the other side, there is a magical spot where you could place a charge, and the force of the 4 microcoulomb charge, pushing it, say, this way, would be exactly equal in magnitude to the force of the 2 microcoulomb charge, pushing it that way. Because the 4 is a bigger charge, so its force extends over a greater distance, you see? So the math told us that there's this spot where the 2 charges are equal and opposite, but there is also this spot where the 2 charges are equal but in the same direction. Of course, this would not satisfy our answer because this would not produce a net force of 0, but we have to remember what we asked for. We asked the math to tell us where the magnitudes were the same. So same magnitude, same direction, but that means that F net is not 0, because if they're working in the same direction, they add up. Over here, we have same magnitude, opposite directions, and so therefore this must be the one where we can have a net force of 0 because they do cancel each other out in the tug of war. And remember, it doesn't matter if it's positive or negative, little red Q here, because it would just mean these would be attractions instead of repulsions. But he canceled out of the mass, so his charge amount and the nature of his charge doesn't even matter. So that's how you can solve a question like that. That's a relatively tricky one. For grade 12, that's probably as hard as it would get. But you'll see this next year quite often if you take physics, and it's a very common kind of question, so I thought we would give an example of how to deal with it.